Hi, okay, welcome to the second lecture in this oculomotor series. I'm going to be talking today about converting those neural signals from place codes to rate codes. This terminology, place code and rate code, isn't something I talked about a great deal in the first lecture, but I talked about the ideas behind it. The slides that I'm using here were developed initially by my colleague Alex Blenkinsop, who's since left the university. Okay, so I'm going to develop ideas from the first lecture on place codes and rate codes. I'll talk a bit about why we need to be able to convert between the two, although really that was the subject of the last lecture. And I'm going to talk about three ways of achieving the conversion and what the expected outputs of each method would be. This is largely based on an excellent paper by Jennifer Groh, which was published 20 years ago, and she wrote down some of the mathematics of the ideas of converting neural signals from place codes to rate codes. Okay, so information enters your brain as a map. This is a kind of recap. The optics of your eye ensures that an image forms on the retina. Then you've got neurons in the brain arranged in sheets in the superior colliculus, and axons, and its retinal ganglion cell axons, grow from the retina into the superior colliculus, and they kind of magically maintain this mapping. You could search retinotectal mapping to find papers on this magic, and there's a huge body of work on that which goes back decades, on how it is that this the mapping is maintained, and it's something that I'm interested in as well, but that's not the subject of today's lecture. So we just accept that the mapping is maintained. It's somewhat distorted, it's somewhat modified, but essentially if objects in the world are close together, then the activity in the superior colliculus is going to be close together. Okay, so this idea that if you have activity at a certain location on the superior colliculus map, then you've got activity in a certain place in the world, we give that name a place code. So essentially, just some activity in a particular location means the stimulus was at a certain location in the world. So there's a place code. But you can't use a place code to drive a muscle, because a muscle, if you drive it with a fast signal, so with a lot of neuron spikes per second, then you will get a large response from the muscle. And if you drive it with a slow response, or just a few spikes per second, then you will get a kind of a weak response. So somehow we need to create a signal for the motor neurons that drive the muscles. And we need this signal to vary over time. We need to, as I discussed in the last lecture, to move the eye, we need to start off with a strong force, and then we can reduce that force down to a constant rate, or a constant sort of moderate force to keep the eye rotated at the desired location. So we call this kind of code, this kind of neural code, a rate code, in the sense that it's the rate of neuron spikes that matters, not which neuron is generating them. Okay, so how do we convert? And this is the slide from the end of the last lecture. How do we go from this kind of place code idea, where we've got sort of hills of activity on some sort of sheet of neurons, and how do we convert to this time-based signal, this rate code? So you kind of think about how you might engineer this kind of system. And if you're thinking about how you might engineer it, you might first of all try and simplify the representation as much as you can. So this image here, which I keep showing from the Otis paper, the 1986 Otis paper, that's showing admittedly a mathematical model of the real retina. But as such, it's a sort of hemicircle, or a semicircle for a hemisphere of vision, and that maps onto a colliculus, a single colliculus, which is this kind of rugby ball shaped sheet of neurons. So we might say, well, let's try and make instead of our world being some circular thing, let's make just a Cartesian world which is rectangular, and then let's make that mapping kind of keep that mapping fairly rectangular. So we'll make this a kind of idealized superior colliculus down here and make it a square thing. It's got activity from the fixation there, it's got activity from the target. We'll just ignore the activity from the fixation. We'll sort of assume that activity is not responded to. And so we'll just take this thing here and say it's a square grid of a superior colliculus, and the activity in a certain region, say here in the circle, is going to be that's going to define the target that we want to move to. In this case, it's in kind of saccade eccentricity r and saccade angle phi, but we could very well simplify it even further and just say, well, let's make that x and y. So here we've got the same idea. We've got this thing. We might say that this is just going to be x and y. It's a Cartesian superior colliculus, and in the case of having a Cartesian superior colliculus, how would we get that to drive a muscle correctly? And thinking in 2 dimensions isn't too difficult, but it's always easier to think in 1 dimension. So let's just forget about the whole 2-dimensionality of the thing, and let's just say, okay, let's have a 1-dimensional row. We'll take the bottom row and we'll just say this is 1 dimension for a horizontal movement. And then let's just reduce it down to 5 neurons, okay? And let's just think about a really nice, simple, single dimension with just 5 neurons, and that's driving 1 muscle. Okay, that might be simple enough to kind of work with, so let's go with that. Okay, so you want to engineer your conversion. You need to think about how these 5 input neurons, I call them an input layer, are going to drive a single output neuron, which is then going to drive the muscles. So let's just say we've got these 5 neurons. They've got what's called a receptive field. So the first neuron is most receptive for a stimulus at 5 degrees along this horizontal range. And then the second neuron is going to be most active for a stimulus at 10 degrees, 15, 20, and then 25 degrees for the 5th neuron. Okay, so the first neuron might be a little bit active for a stimulus at 10 degrees, but it will be much less active than the second neuron. If you've got a stimulus that lands between the two at, say, 7.5 degrees, then both the first and the second neuron will both be active, but not as active as if they were being driven for their preferred angle. Okay. So if we imagine a stimulus, a light flash at 20 degrees, that will cause activity mostly in the 4th neuron, and somehow we want that to drive the output neuron. And we want the firing rate of the output neuron to be small for small movements, so small for a 5 degree movement, and we want it to be large for a 25 degree movement. And we want that firing rate to increase monotonically related to the target eccentricity. It doesn't necessarily have to be linear, but it does need to, every time the input gets larger, the output neuron firing rate needs to get larger. I haven't mentioned the way that the input layer neurons are connected to the output neuron. Essentially, that's the task we have to figure out. In what way is this connection achieved? And are there any other neurons in between that are, or components of any sort, doing something for us in between those, the input and the output? Okay, so one way we might connect the neurons up is just to simply connect an axon, connect a wire from every single input neuron, and connect each one to the output neuron, but with varying weights. So the connection from the fifth neuron is the strongest connection, and the connection from the first neuron is the weakest connection. So that's the idea there, and then we're looking for this output rate code where, as the position increases, the firing rate of this output neuron also increases, hence the increasing weights of these connections. So we'll let the weights be proportional to the target eccentricity. So this first neuron's preferred target is it's maximally active for a target at 5 degrees, so we'll give it a weight 5, and then we'll increment the weight by 5 for each one until we get to the fifth neuron, which is maximally active for a 25 degree stimulus, so we'll give it a weight of 25. And then we actually work out the output of that output neuron by simply taking each neuron and axon as a pair, and we multiply the activity of the neuron by its weight and add all of those up. So it's activity times weight 1, activity 2 times weight 2, activity 3 times weight 3, and so on until we get to the end. Okay, this is just a shorthand way of writing that. It's the sum over all neurons, of weight I times activity I. So we can imagine what the sum is, or we can do the sum for our 20 degree stimulus here, and we'll just assume that is a stimulus of value 1. Okay, and then the output of the output, or the rate of the output neuron, is going to be 0 times the first, 0 times the second, 0 times the third weight, 1 times the fourth weight, which is 20, plus 0 times the fifth weight. So that's very simply 20 hertz. We'll call it hertz because it's in spikes per second. So we've got a rate of 20 hertz, and let's imagine that 20 hertz firing rate moves the muscle to move the eye to a position of 20 degrees. So we can apply the same sum if the stimulus is at 10 degrees. And in this case, we're going to have 0 times all of the weights, except for 1. Our stimulus size is still 1. We have 1 times 10, which is the weight of the second neuron. So that's giving us a firing rate of 10 hertz in the output neuron. 10 hertz for a 10 degree movement sounds plausible if 20 hertz gave a 20 degree movement. So that all sounds fairly good, right? It sounds like this might be a winner. So maybe weighted summation is all we need, and we can go home. Job done. There is a problem though, and the problem occurs when you imagine two targets, or rather two stimuli. So if we now say that there's a stimulus at 20 degrees and a stimulus at 10 degrees, and we do the sum over all of those neurons, now we've essentially got 1 times 10 plus 1 times 20, which gives us a 30 hertz firing rate. Now, it's not clear what a good output should be for this eye movement. I mean, maybe we should move to the closest stimulus, maybe we should move to the stimulus that's furthest away, maybe we should make some decision randomly on which one to move to, or maybe we should saccade to some average point in between the two. But it seems pretty likely that we shouldn't kind of overshoot both of the stimuli and land up at 30 degrees, or so that seems like it's not good, right? And there's another problem, which is that if we reduce the stimulus size by making the target dimmer, we have another problem. So suppose we've got a dim target now, which has a luminance of 0.2, 1/5 of the luminance, and it's at 10 degrees. our sum here now is 0.2 times 10, which gives us a 2 Hertz firing rate. And so we're going to undershoot. We're only going to get, suppose we may only get to 2 degrees instead of 10 degrees. So this is a pretty big problem with this weighted summation approach. So presumably the brain is doing something a bit more sophisticated than this in order to control eye movements. But if the brain did do it this way, what would we see in the output? Let's just imagine the graph that we would see if we plotted the firing rate in the place-coded sheet versus the output firing rate of that output neuron which is driving the muscle. So at location 1, which is the short saccade, we would see as the activity in the input, so this is essentially as the luminance of the stimulus increased, so would the output firing rate increase at this slope rate, if we had a stimulus at the second location, which is the 20-degree location, then we'd see, because the weight of that connection is larger, the output firing rate would increase with a steeper gradient for the same input sort of luminances. So we'd get some sort of graph that looked like this for location 1 and a graph like this for location 2. And then if we had both stimuli present at the same time, we would see an output firing rate which was the sum of the two inputs. So it would actually be larger for all firing rates of the input neurons. Okay, so it's essentially the sum of the two. Okay, so there's these two problems of multiple targets and the target luminance to get around with the weighted summation approach. So one approach would be to suppress all of the other stimuli. So you essentially choose the neuron which is the most active, and you get that most active neuron to suppress all of the other neurons in the input layer. That's called a winner-takes-all process. And once you've got a winning neuron, then that's the single neuron which, if you allow it to saturate at some maximum firing rate, it can then drive the muscle using its weighted connection to the output neuron. So you do this by having kind of connections between neurons within the input layer, the place-coded sheet. Or you could have an alternative approach where you have some sort of selection mechanism, such as the basal ganglia, which is essentially connected into that place-coded sheet and is kind of doing the decision process for you. But it still doesn't really solve the problem of how target luminances are varying, unless you, as I said, you have some sort of mechanism by which you maximize the firing in that place code. But there is one approach we could use to get around both these problems, and it's called weighted averaging. So mathematically, what we do is we normalize the firing in the input layer. So we take the original approach, which was this sum of the weighted activities, which is the top part of that sum on the right here, that equation on the right here, and we divide it by the sum of the activities. So that's essentially the total activity in the place-coded sheet. So if we apply that sum to generate the output of a weighted average system, what we do then is we get, so we're doing the sum, imagining that we've got our two stimuli at 10 degrees and 20 degrees. So our output is going to be 1 times 10 plus 1 times 20, which is 30. But it's going to be divided by the sum of the input luminances, which is just 1 plus 1, which is 2, and the final result is that we get a 15 Hertz rate. Now 15 Hertz, if 10 Hertz gave us 10 degrees and 20 Hertz gave us 20 degrees, then 15 Hertz presumably gives us about 15 degrees, which is an average position between the two. And that's exactly what you see in experiments, is that if you have two stimuli, then the initial saccade will tend to land between the two stimuli. So this is good, right? So yeah, there we are, correct saccade. Oh, sorry. Yeah, so we go back to a single stimulus at 10 degrees, but this time we've got a stimulus which is has an intensity of 0.2, so it's a dim stimulus. So now our output is going to be 0.2 times the 10, which gives us a total of 2 on the top of the equation. But now the total sum of all the activity is only 0.2, so we divide it by 0.2. That gives us a 10 Hertz output rate, and that gives us a correct saccade as well. So this normalization approach seems to solve both the multiple stimuli problem and the stimulus intensity problem. So the question then is how you would actually implement the maths of averaging, of doing the normalization in using neurons. And the answer is to have a denominator channel. So now we've got a sort of slightly different kind of diagram where we've got our input layer here of 5 neurons at the top, and we've got our output neuron here, which is generating our rate code, and we've got our weighted connections through to this. So we've got a sort of intermediate neuron here, which is collecting up and doing the weighted summation. So this is giving us the result of the weighted summation. But in addition to connecting through to this summation neuron, the input layer is also connected to a denominator channel, only this time instead of having varying weights, it's got just the same weight for every connection. So this neuron here is adding up the activity in our input layer, and this is producing the weighted sum. And then we take this number here and we divide it somehow by this denominator number here, which gives us the rate code that we want. So what's the problem with this? So one thing is that this denominator channel all has to feed into a single neuron, because then that single number has to be divided in a single operation. We can't sort of, it's not like adding up where we can add using multiple connections. It's a single division operation. It's also not clear how division really occurs with neurons. But there's a second problem, which is that the dynamic range of the denominator neuron, i.e. this guy here, its dynamic range has to be huge, and I'm going to explain that in the next slide. Okay, so let's say we've got some sort of input where we've got an input luminance of 0.1 on the third neuron here. So let's say that each place code neuron can have activities between 0 and 1, and we'll say that we'll just divide that up into sort of 10 values, so it can be 0.1, 0.2 and so on up to 1. So in order for this network to function, the denominator channel has to be able to distinguish between no activity at all, with all of the input place code neurons having 0 output or 0 activity, and then it has to be able to tell the difference between that and any one of them having a value of 0.1. Okay, and we'll say that it can do that. Okay, because that's basically what we're saying, is that it needs to be able to say if if we've got a 10% of the dynamic range of one place code neuron, then we're going to recognize that as being a value. So yeah, that's basically what this says here. So 10% of the dynamic range of a place code neuron to get some sort of response. And that means that if you had, suppose that place code neuron had a certain amount of noise on it, maybe it would fluctuate by, a few percent, 5% or something, then the idea is that fluctuation wouldn't be picked up by the denominator channel. But suppose we say, okay, now all of our input neurons in the input layer, instead of them being 0, 0, 0.1, 0 and 0, we're just going to add 0.9 to all of them to sort of up the overall activity. So they've got a kind of constant offset of 0.9. And that's not particularly unusual in the brain. There's a lot of sort of tonic activity goes on in neurons. They're not necessarily completely silent and then they're active when they've got a signal. Sometimes it's just levels of activity. So that denominator channel has got to be able to discriminate between all of the inputs being 0.9, which means essentially no input, and all of them being 0.9 except for one of them having its maximum output of 0.9. So it's got to discriminate between the value of 4.5, so if we add up all 0.9s, then the denominator channel is going to have 4.5 on it, and then it's also got to be able to tell the difference between 4.5 and 4.6, which is if they're all 0.9 except for the one of them is 1, and it's a small difference in the number 4.5 to 4.6, but it's essentially the difference between no movement, no saccade, and a saccade to 15 degrees. Okay, so if we work out what proportion the difference between those two is of the total, then we find that it's 2% of the input range. And now if we've got 5% of noise on any of those neurons, then you can see we're going to start getting errors in the conversion. So this is kind of a problem. And in general, the dynamic range that you're going to need in that denominator neuron is going to be n times the dynamic range of a single place code neuron, where n is the number of neurons in the sheet. And in a real brain, that n is going to be thousands or tens of thousands of neurons or more. So that's going to be a very large number. So you need this huge dynamic range to be able to distinguish between small differences in the input map in this denominator channel if we're going to use this weighted averaging scheme. Okay, so a possible solution to the achieving weighted averaging that some authors have suggested, and Groh refers to this in the paper on page 161, is to use lateral inhibition to achieve the normalization. So this is, if you search normalization and lateral inhibition, or lateral inhibition and division on a Google Scholar search or something similar, you'll come up with lots and lots of papers. But the idea is that you have within the sheet of neurons, you've got one neuron which inhibits all of the other neurons when it's active. But it's not just this neuron that inhibits these neurons. Every one of these neurons has the same pattern projecting to all the others. This essentially achieves a kind of normalization. Mathematically it achieves this, where it divides the activity by the sum of the activities of the other neurons before summing up and multiplying by the weights in the connections. So you can compare it with the regular weighted averaging equation here, which you saw a few slides earlier. So there is evidence that this occurs in the brain. So, for example, the retina, it's this kind of lateral inhibition for normalization occurs in the retina, and in the visual cortex, it's used in some cases not just in a feature-based way or in a location-based way. I'm sorry, where the inhibition is between neurons that are close to each other in a map, but it can also be features, so that certain features in a piece of brain tissue will. So neurons that recognize a certain feature, a certain visual feature, like an edge at a particular angle, will suppress neurons that are active for edges at different angles or different structures, different features rather. Okay, so there is evidence that it occurs in the brain, but it probably isn't the reason for the normalization in the colliculus. And one piece of evidence that Groh remarks on is that you can stimulate frontal eye field in one location. So if you remember that we've got many different maps driving the output of the eye. So if this one represents the superior colliculus, we could have another 5 neurons that represented our frontal eye fields. And those frontal eye field neurons do have an effect on the output. They do feed into the system. And one thing that you can show experimentally, is that you could, in the frontal eye field map, you could stimulate the first neuron, and in the superior colliculus map, you could stimulate the 5th neuron, and you will still get an averaged saccade. So if the normalization was only occurring, say, in the superior colliculus, then you wouldn't expect to see that normalization come out with the average saccade. You might expect just to see either the neuron that was activated in the colliculus taking precedence, or the one in the frontal eye fields. But if your mechanism was only within each layer, then you wouldn't expect to see that average saccade. So, okay, let's go back to the graph of the output firing rate versus the firing rate in a place-coded neuron, and just go through that process of considering what happens for individual stimuli and multiple stimuli. So if we go for location number 1, so the weighted average. So this is a flat line, because as the firing rate at location 1 increases, we're still dividing by the total activity in the sheet. So we get just a fixed output firing rate for activity at location 1. And if we go to location 2, we get a higher output firing rate, but it's fixed for location 2. And if we have both of the stimuli at the same time, then we get an average firing rate in between the two. And again, it's constant. It's immune to the change in the input stimuli luminance. So that looks pretty good. So just before we go on, you might say, well, why not just go with the vector averaging approach? Is that not just going to work? And the problem is really the division. It's the division step. It's not clear. If we go back, actually, just to a picture. Here we are. If we go back to this picture here, this is supposed to be doing division. So we've got some number which is the sum of the activities. So we've got a number coming here. Suppose it's, well, in this case it's like 4 or something. And we've got some number coming out of here, which is the weighted sum. So I know, suppose that's 35. And somehow that's got to be turned into 35 divided by 4.5 or whatever. And it's just not clear how this neuron is supposed to do that, how it's supposed to achieve that. It's just a sort of magical mathematical step. So we really need to, I mean, although mathematically this approach works, we need to find a more kind of biologically plausible way of implementing it that we could imagine, real biological neurons achieving. So let's go back to... Okay, so the question is, can we get rid of it? So we go back to the first model. So this was the graph of, for the first model, just the simple weighted summation. This was the activity in the place-coded sheet on the input versus the output firing rate, and it was fine. It was kind of okay if you took a fixed activity. You would then get, you could get a sensible size saccade for a luminance at location 1 and a sensible size saccade for a luminance at location 2, but you add them together and you got an overshot saccade. But what if we could say, as the activity, suppose we could sort of count the number of spikes as we went up that curve and truncate it after we'd had a certain number of neural spikes. So let's just see what that would look like there. So what we do then is we say, so after a certain number of spikes, we truncate the activity and we just take that as being the final output firing rate for the output neuron. And what we see is something that starts to look kind of usable, because the combined effect of the two luminances is actually now landing in between 1 and 2, so the short 10-degree saccade and the 20-degree saccade. So this would kind of give us a kind of normalization by the back door. So that's what we're going to do. What we're going to do is we're going to slightly modify the vector averaging approach, or the saccade averaging approach, and we're going to take each of the neurons in the input layer. We're going to wire them into this neuron, which is now an integrator neuron. And it's not just adding up the instantaneous activity of the activity in the place code, but it's summing up all the sort of historical activity in that input layer. And it does that with this recurrent connection back here. So as soon as you get this neuron going, it feeds back on itself and it keeps itself going by that amount. Okay. And then we feed the output of the integrator into this inhibitory interneuron. Let's just see if there's any more. Yeah, okay. Okay, so now we also take this weighted summation neuron and we turn that into an integrator as well. So it's kind of keeping a historical average of the input, the place code, of the weighted sum. Okay. I'll just move myself up there. And then finally what we do is we take the activity, the integrated activity here, and we feed it into another neuron. And the difference between this neuron and that neuron is that this one is sending out an excitation, and this one here is sending out an inhibition. So as there's more activity here, we set off this inhibitory interneuron. And what we do is we give this a threshold. So we say, okay, when the integrator gets to some value, I don't know, 10, then this one becomes active and it suppresses all of these inputs, essentially suppressing them perfectly. Okay, and that has the effect of stopping any more activity from the place code feeding into this neuron here. This neuron here, because it's self-excitatory, just keeps itself going with whatever rate it had summed up, and it then feeds into the final output neuron, which is going to drive the muscle. There we are. leaving only the integrated signal. So the denominator channel effectively counts the number of spikes, and it shuts off the numerator channel when a fixed number of spikes has been fired in the place-coded sheet. So here we go. We're going to suppose the interneuron threshold is 20 spikes, and we're going to suppose that the neuron at location 1 fires at 10 Hz. So here we are. This is the number of spikes in the place-coded sheet on the x-axis. And so after 2 seconds, because it's firing at 10 Hz, 20 spikes have been fired. And if the threshold is 20 spikes, then the inhibitory interneurons just shut it off now, and they prevent it increasing anymore. So the output firing rate stops there. And then it goes flat at that point. And then we have the same sort of thing. So we say that there's the same firing rate at location 2 as for location 1. So the question is, why does the output associated with location 2 increase more quickly than for location 1? And the answer is because of the additional weight on that channel for location 2. So the additional weight, although its activity builds up to the 20 threshold at the same time as the activity gets to the threshold for location 1, the output firing rate increases faster because of the increased weight. So that's why it gets a higher final value, which is what we want. We want a higher value to drive the muscle with. So now the condition which we stimulate both regions at the same time. Why is the slope steeper? Well, it's steeper because we're driving 2 neurons now. They're both contributing spikes. So it's a steeper slope, but because we're driving 2 stimuli, we're actually going to get to that threshold of 20 spikes more quickly, in half the time. So that's why it's much earlier that we stop increasing and we go to the final constant output value, and that's how we get our average output. So there you are. I think that's what I just said. Okay, so that's a sort of that's a more biologically plausible approach that kind of achieves division, but doing it in a summation with saturation way.